Okay, cool. Let's get started. Hi everyone, my name is Kai from Confluent. I will talk today about serverless Kafka and Spark in a Lakehouse architecture. So that's a lot of buzzwords in the title, right? So no worries. So this is really about real world experiences from our customers and what we see around the world, how the journey is going towards the cloud, towards a modern technology stack. And I will also show a few real world examples from deployments. I will show the pros and cons and also talk about when not to use a specific technology. And that's the main intentions of this talk in the next 30 minutes or so. Therefore, I have a packed agenda, as you see here, each topic around 5 minutes or so. So to really explain when to use the right technologies and what they can help with best. So we will talk about data analytics at rest, data streaming in motion, and then most interestingly, of course, how to combine these technologies and when to use what for the right approach. And as I've mentioned, I will also show a few concrete examples how that can look like. For example, specifically, I'm using an IoT use case with connected cars, so that you see how you can leverage real-time analytics and also data warehousing and other things together. And so with that, let's get started with the first point about data analytics at rest. So this is really typically the foundation also how most people think about technology today still. And what that means is in the end that, well, you store data at rest, which means you put it in some kind of storage system. So this could be an Oracle or MySQL database, or of course today we're more talking about a data lake or data warehouse. So we store data there so that can be analyzed afterwards. And this means typically when we have data stored at rest, well, then we write a query or use some other API to get data out of there, to use it to find insights, to do complex processing, or whatever you want to do with the data. But really that is what it means. You get data in, you store it somewhere, and then you use it later for processing for some kind of use case. That's what we mean with data at rest. And now, for data at rest, there's plenty of use cases, right? I mean, we see this across all the conference here today and tomorrow. There is these traditional business intelligence use cases like reporting, where you use a tool like Looker or Tableau, where you do some queries and then you create some great dashboards, and then either you do weekly reports on that, or maybe you find some new insights with more interactive queries. And then more big data use cases are around data engineering, machine learning, training analytic models. That's always when you take a look at historical data that's stored at rest, and then you take it to do some analytics with that for very different use cases, very different business people, technologists are using that, and with that, of course, a lot of different technologies come into play for that. So there's many different options for how to do things with data at rest. Now, here, of course, at the Data and AI Summit, we're talking a lot about Apache Spark. And so this is still what I would say the de facto standard for big data at rest. I mean, we started many years ago with Hadoop and MapReduce, but then in very early stages already we came to Spark because it worked much better for many of the use cases. But still, if you think about that, the story is the same. So we get a lot of data into the system, either with batch ETL tools or with an ingestion tool like Kafka and more in real time, and then we put it there in a storage. So years ago, we all used HDFS for that. Now we're typically using an object store under the hood. If you're using a cloud service, we don't even see what we're using and we don't care. We just use it to do analytics on top of that, to get from historical data into insights. And this can be insights like building an analytic model with machine learning, create a report for BI, or maybe do some more near real-time or real-time analytics on top of that. So there's a lot of options. And now, I mean, we've heard this a lot in the keynote today and in other sessions. Then we also have to think about things like the structure of the data and use open data formats so that different technologies and products can speak with each other. And obviously, as we've also seen in the keynote, the growth and the adoption of the technology like data lake, this is really key so that you can also let different applications talk to each other with the data at rest. Because typically it's not just one interface, right? Like the data scientists typically use something like Python and a Jupyter notebook to connect to the data. While maybe, for example, a Kafka developer uses a Java API or another system to connect to the data. So you need to understand how to store the data and to use the right formats so that everybody more or less speaks the same language with the data at rest. So this is now what we have known for a long time, right? We store data at rest. However, and that's also what we've heard in the keynote, right? More and more use cases require real-time data processing. So, and that's in the end where we're coming to data in motion. And so why do we see that coming up so much more these days? Well, in the end, it's a very easy answer to you. So reality is that real-time data beats slow data in most use cases. So forget the technologies under the hood, but think about the business case and ask yourself or ask your business teams if you're a developer or architect, if you can get access to the data now and use it or use it later. Whatever later means, it can mean minutes later, hours later, days later, weeks later. What's better for your business if you can take it now or later? And in most cases, the business will tell you, well, of course, now is better than later, right? So here's a few use cases for that. And this is just really just general use cases across different industries. And in some cases, real-time is not mandatory, but it's still already better than doing it later. So for example, if you want to do personalized offerings or recommendations in an e-commerce platform or in a location-based service while you're walking through the store, or whatever your use case is. So it's not mandatory to be real-time, but it's better for the customer experience because you get push notifications when they are relevant. And also it's typically better for your business because you want to upsell while the customer is still on the website or in the store. Because when he has left the store, the chances are very high that he buys the next product from a competitor and not from you. So real-time beats slow data in these kind of use cases. And then obviously there's other use cases where real-time is mandatory. Think about fraud detection. Fraud detection, if it's not real-time, it doesn't make any sense. I mean, yes, of course, you can get all the payment information into your data lake and store it there and process it overnight in a batch process. You will still find out that the fraud happened, but that doesn't help that much anymore because the fraud happened and you already lost the money. And so therefore, for some use cases, real-time processing, and here we're really talking about typically then low latency with milliseconds or maybe less than a second, is critical for the success of the business case. And so with that, in summary, real-time data beats slow data. And this is where it's a foundational paradigm shift about how you think about data. So with data at rest, as I said before, we ingest it first, we store it on a disk, in a data lake, on an object store, and then we do queries against it. On the other side, with data in motion, it's really turning the things around. The data is flowing through the system continuously, and you're acting on that while it's in motion and while it's interesting. And still, on top of that, we can still do queries, of course, and do other things, either again in real time or maybe in batch for analytics. But the foundation of the data layer is streaming data and not data at rest anymore. And so to take a look at this from another example, right? So here is now a table at rest. So this is what you store in a database or in your data lake or in your data warehouse. So this is about payments, and for every new payment, we store this information at rest in the database table. Now, on the other side, if we take a look at this from a stream in motion, this is in the end, each event is its own information that you can take and act on. It's not like you always take a look at the whole table or query a specific ID from the table. It's each stream which is independent of each other and you act on that, or you correlate it with other streams. So it's a very different paradigm about how to use data for very different use cases often. And now if we combine this together, and this is now the most interesting part, and this is actually what we typically define as data streaming or streaming analytics or stream processing. So here in this case, on the right side in orange, you see the table. So this is in the end data at rest. So this is, for example, a credit score, right? And then on the left side in blue, when we do a new payment, this is a real-time stream, each event by itself. Then we take action on that. And in this case, for example, one of the actions is that we recalculate a credit score, which is data at rest. And with this, you combine the information of historical data and take action on that by new events. And this is super critical because with that, you get the most power out of data by correlating real-time and historical information. And this is typically what we mean with data streaming or real-time data. So the big added value of real-time data is not just getting data from A to B somehow, right? That's not added value. The added value is to correlate this information with other information in real time. And that's also why I'm always explaining that when we talk about technologies, similarly like we talked about Apache Spark for mostly data at rest, when we talk about data in motion and Apache Kafka as the de facto standard for that, the first thing I tell people, well, and I heard this actually several times again today at this conference, right, where people talk about Kafka as a message bus. I mean, yes, you can use Kafka to get data from A to B, like from your data sources into your data warehouse or data lake, and that's totally fine as a use case for data ingestion. But what many people are not aware of is that Kafka itself as a streaming platform is much more than that. So number one, Kafka is, yes, messaging, streaming, a message queue or whatever you called it. You get data from A to B in real time. That can be big data analytics, like in Confluent Cloud, for example, we have customers that process more than 10 gigabytes with a single Kafka cluster. So that's high volumes of analytics workloads in real time. On the other side, it's also for transactional workloads, like a payment information, where the SLAs are very different from an analytics use case. However, Kafka is much more than that. So also Kafka is a storage system. And this is huge for some characteristics and use cases, because you store all these events in Kafka as long as you want to store them. For your favorite ingestion use cases into the data warehouse or data lake, of course, the retention time is only a few hours typically, or maybe a few days, because after you ingested it into the data at rest, you don't need it anymore in the streaming layer, right? So for this use case, that's totally fine. However, for other use cases, when you build real-time application, like the next fraud detection or payment platform, well, then it looks a little bit differently, because then it's more about keeping the data longer here so that you can also replay it later. Or when you want to take a look at historical data for compliance reasons. So there is reasons where you store it longer. And another reason why you store it longer is for the true decoupling between the systems. Because Kafka with that also handles the back pressure, right? Not everything in a high volume can be ingested in real time into every system on the data sync side. So it depends on where you ingest it into, right? But in most cases when people use Kafka, they are not just using it for one data sync. They're using it for very different data syncs. Like in addition to ingesting all the raw data into a Databricks cluster for further analytics at rest, they also build real-time applications around that. Or maybe they also use Elasticsearch because it's for completely different use cases where simply a search engine is the better tool than a data lake. So it's typically more like a best-of-breed approach. So, and Kafka with the true decoupling of the systems with the storage is very different than a message queue. And now we're still not done here, right? Kafka is also a data integration platform with Kafka Connect. So most of our customers, obviously, when they use tools like Databricks or Elasticsearch, they also use the integration capabilities of Kafka to connect to these systems. Because then you don't have to worry about what happens in case of failure. How do you scale the data integration? How do you guarantee the ordering of the events you get into the data lake? With Kafka Connect, all of that is built into the system. So you don't need yet another ETL system between the data ingestion layer Kafka and between the data lake, like Databricks, right? You can't do that with Kafka. And last but not least, Kafka is also a stream processing framework. So you can correlate data and take action on different systems. And again, this is typically the secret sauce for the business value where you can add more value into such an application. You don't get business value getting data very fast into a data warehouse. You get the business value when you can take action on that in real time or near real time. And then depending on the use case, sometimes you do a query in near real time on the data warehouse, but sometimes it's really about low latency or critical scale, where then you do it directly with Kafka. So in summary, Kafka is much more than a messaging system, right? That's in the end the TLDR here. And so with this was now really to setting the context, right? On the one side, we're talking about data at rest, putting it somewhere to do queries and analytics. And on the other side, we're talking about data in motion to continuously processing and correlating data. These concepts are independent of technologies, right? So of course, you can also use other things like Kafka or other things than Databricks, or maybe combine them somehow. And that's in the end, I think also what we hear a lot at this conference where the Lakehouse comes into play as a new paradigm so that you can leverage data the right way, depending on your use case. So when I was saying real-time data beats slow data, and if you ask the business, that's true for many use cases. But obviously, there are some other use cases where you need to correlate batch workloads, like for a report of the last week, like for training an analytic model. That's a batch workload, right? And that's what you do in your data lake, of course. And therefore, I really like, and we have seen this in the keynote, that it's not just Databricks, but many vendors talking about how to build a lakehouse, right? Like all the cloud providers, or this bad other big data warehouse vendor in the cloud, right? So all of them are talking about the data lake and data warehouse. And with that, the lakehouse, which is in the end a combination of them. So what I, however, also want to emphasize really, and maybe not everyone agrees on that from a vendor perspective, but in my opinion, a lakehouse is still a logical point of view. It's not a physical point of view, because you really should choose the right technologies for solving the problem, and with that building your data lakehouse, whatever the technologies are for that. And so how have you seen building such an architecture in the past? I guess most of you in this room here at this conference know very well what the Lambda architecture is, right? Because this was typically what we were trained how to build such a data lake, or today a lakehouse. So this means on the one side we build a batch layer if we want to get batch workloads out of a system and get it into the data lake. And on the other side we also have a real-time layer, very often Kafka then, to get real-time data from A to B as an ingestion layer. And then on the right side we build our applications. Some are real-time, some are batch. In this example here, we have built a serving layer in the middle as part of the Lambda architecture because, unfortunately, and this is what in the real world typically happens, people find out, well, it's great if we have real-time data here and batch data here, but the real added value comes when we can correlate the data so that we can use the information of both of them together. And this can be for one data feed where we processed the initial load in batch but then get real-time data and the value comes out of both of them. Or if we correlate real-time data from one system and correlate it with historical data from another system. That's also a very common use case. The other option for the Lambda architecture is we still keep it completely separate, right? We build a speed view and we build a batch view. However then, we are still in the end offloading this kind of correlation of both together into the right side, into the application where we have to do the mixed query then for many use cases. No matter which of these two architecture types we choose, there's one challenge with the Lambda architecture. And the challenge is that we have two completely separate infrastructures for doing batch and real-time, right? And in the end, this is the same what you have seen from the Lakehouse architecture in the keynote, right? Where you should build in the end a lakehouse for doing that, can do real-time and batch. But where maybe also I disagree with some other people is where I think this is not a single technology and it shouldn't be, right? So therefore, what we see a lot now in the real world, and I will show you an example in a minute too, is that more and more people start talking about the Kappa architecture. So instead of Lambda, where you have separate batch and real-time workloads, we still have batch and real-time workloads. That's the funny part about that, because as I said, both are very relevant for your use cases. Choose the right one for the right problem. If real-time beats slow data for your use case and adds business value, like increased revenue, better customer experience, reduced risk, well, then you should build a real-time application. But for some other use cases like reporting and training analytic models, that's a batch workload. However, the big difference in this architecture is that you don't have two separate integration and ingestion layers. So the question here is, why do you need separate layers actually? So if you get all the feeds into a streaming layer first, right? As I said, on the right side you see the picture. You can still do real-time and batch. You can decide this by domain, by business, by application. But you don't have separate infrastructures for the integration layer. And the most important thing here, what people often underestimate, if you first get all the batch data into a batch system, then it's at rest. You cannot connect a real-time consumer to batch data. This is one of the most important things to understand, right? I've attended several other talks here, and what's a bit amazing is then typically when people talk about stream processing and real-time data, the first thing they're doing, they're getting it out of S3 object stores. I mean, I'm sorry, but then the data is already addressed, it's stored on disk, right? This is okay if you define real-time as something which takes seconds or minutes, then yes, right? That's why it's important to understand the term real-time. But if you directly process the data in the streaming layer, that's in memory. It's still persisted on disk for the availability and no data loss, but you process it in milliseconds from memory. As soon as you go to an S3 object store, it's not real-time anymore, right? And so this is really important to understand depending on the requirements of your use case. And this is where now with the Kappa architecture, you can choose this per use case, how to connect to the systems and how to build the applications with that then. And here's a real world example for that. So, and by the way, in the meantime, there's many of them, right? So we were very lucky at the last Kafka summits where we had several examples. This is one from Uber here, which shows exactly what I showed more in a theoretical way and here in a real world example. Here you see they're getting all the data into Kafka, right? And note that on the left side, the data they're connecting to, not all of that is real-time data, actually. They are also getting data out of a database and push changes into Kafka. So I attended another talk an hour ago about Debezium, right? As one change data capture technology, like Robinhood, I think was doing that, right? And also other applications like the Rider app and the Driver app, that's not a native streaming interface. That's in most cases a REST API. You connect via proxy into Kafka. But as soon as an event happens somewhere, you get it into the streaming layer. And then on the right side, the business can make the decision how to process the data. And if there is more value processing it in real time, well, then you should process it in motion and not at rest. However, for other use cases like you see here, and I mean in the case of Uber, they're using a lot of Hadoop still, right? But it's the same story like with Databricks, for example. For ad hoc exploration, for analytic reporting, for machine learning, that's where the data lake is the perfect data at rest for that. And now, just to give you one example here, right? So this is now an example architecture. When we do this together from Confluent, now where I work for, and with Databricks, our strategic partner for these kind of use cases, how to build such a lakehouse. Well, the point here is, right, of course you combine them. So you have data streaming and you have a lakehouse or a data warehouse or delta lake or whatever you call that, right? It's just the buzzwords in the end. But the point is you can choose the right technology for the right problem and combine them together. And the other beauty about this is with open source and with all these frameworks we are using here, you always have the freedom of choice. And that's true on every level here. So on the data streaming level, of course, for example, if you're working with Confluent, many of our customers are using then Kafka streams or KSQL for the stream processing. However, of course, if you're using Apache Flink as a third-party tool, that's totally fine and valid. And if it's the best for the use case, you should do that for your business application. And the same if you take a look at Databricks here, I mean, you see, they're building some stuff by themselves and then you can connect to other tools, like for example, to Tableau for BI use cases. Or you use TensorFlow instead of just Spark ML for a use case, if it's better for that. Like maybe for deep learning, right, where TensorFlow might be the better approach sometimes. And so you have the flexibility of choice, but still connect data streaming and data at rest with this the right way. And so with this, let me now come to a concrete example, because this is still a bit theoretical, I would say. So let's now take a look and think about a connected car infrastructure. And even if you're in any other business, right, maybe you have a different interface to get data in, but the main story is very similar. And here, let's take a look at Audi, for example. Audi is an amazing example. So they actually talked at a Kafka summit around 5 years ago. So it was one of the first Kafka summits, and that's where they started building a connected car infrastructure. And why I really like this use case here is because even at that time, Audi already had 2 separate Kafka clusters. So why that? One was the integration Kafka cluster, where they got all the data in from the connected cars in real time. This cluster has mission-critical SLAs. It has to have 0 downtime and to run and operate with very low latency. And from that, in the end, the first thing they did, they replicated the data in real time into an analytics Kafka cluster. That's what they call here in this picture the AC/DC platform. And the only idea for the AC/DC Kafka cluster was to get the data into the data lake, to do the batch analytics, to do the reporting on that, to do the explorative analysis and so on, right? So this is what you see in the architecture here. I don't want to go into detail. The point is just you see what as expected. So it's a combination of getting data in from the connected cars, which is in this case natural streaming data. And you also connect to other systems in the back end, like your CRM system, your loyalty platform, your payment third-party integration. And then depending on the use case, you directly build real-time applications in the streaming layer. And in parallel, you get all the raw data into your data lake. In this case, as you see here, it's Apache Spark, right? So that then you can do your analytics there. So it's a perfect combination of data in motion and data at rest. And so to go a little bit more into the architecture, how can that look like, right? First of all, it's important you can choose the right technology points, right? And most of our customers actually start with one first pipeline. Like, for example, getting all the car sensors into a real-time UI to do some monitoring as a first quick win. But then you build more and more consumers around that. And in this example here, you see how this is typically combined at our customers, right? So in this case, you get the car data in via some kind of proxy, like MQTT in this case. And then you have it in the streaming layer. For some use cases, you do some streaming workloads, like maybe the first streaming ETL. And then every other consumer can tap into the data. In this case, in the middle, you see how Spark is used for model training. So in this example, actually, the data can go into the data lake for that, right? For doing the batch training. We have also customers which are doing direct connection between TensorFlow with the Kafka interface and directly consume data from Kafka for model training. Just choose what you need and the right architecture for that. But here now in this example, we're getting the data into the data lake and use Spark for model training. So this is a batch process. It's also not 100% mission critical, right? If the batch process for training the model goes down, it's not a disaster, right? But on the other side, let's assume we build a predictive maintenance model here in the batch process. Well, this predictive maintenance should be deployed in real-time workloads, because if you're tracking the car sensor data in real time for hundreds of thousands of cars and want to detect if the car engine is braking, right, by sensor analytics in real time with analytic models, this should not be addressed, because this should continuously evaluate the sensor data coming in and applying the model to that. And therefore, in this example here, we are deploying the model we trained in the data lake, but we are deploying this model into the streaming application. And in this case, the streaming application has very different SLAs. It's typically then much more mission critical and regarding low latency and availability than the model training, which you can again restart. But if your predictive application is down for real-time predictions, well, if it's down for 2 hours, then you might have problems with a few customers because their engine is braking right now, right? And this is for every use case, like if you think about fraud detection, upselling for customers, whatever the use cases are. And then, completely independent of that, on the right side, at the bottom you see, we're also using Spark SQL here for reporting. So this is the traditional business intelligence, right? Or we also have built another example where we use MongoDB here for building a digital twin. It's always the separation of concerns, because for that use case, MongoDB was the perfect application, completely independent of, separated from these other workloads. Because Kafka in the middle is not just a message queue, but also decoupling the systems. One consumer is real-time, another one is near real-time, the third one is batch, and the fourth one is a request-response web API that connects to Kafka. And so with that then, as I just explained, right, it's separation of concerns, like we are doing the model training in a batch process with Spark. On the other side, the model deployment, in this example here, we did it with KSQL, where we embedded the analytic model, which we trained before in the data lake, but we embedded it into the mission-critical real-time application with Kafka. So this scales on a very different way with different SLAs, often a different operations team than the data lake. And with that, really, I don't want to start a flame war here, right? Because there's so much discussions then which is the better tool for a specific problem, right? There is obviously always some overlappings between these products. Like if you compare and take together Confluent and Databricks as one example, of course you find these 10% of features that overlap, right? So you can do some of the stream processing in Kafka, you can do some of the stream processing in the Delta Lake, right? Or with the Lakehouse, with Databricks. They all have their pros and cons. It depends on the use case. Like for the Kafka applications, I would say it's a little bit more separated from the other workloads, a bit more mission critical very often, or lower latency. On the other side, if you take a look at Spark, it's perfectly integrated into the rest of the data lake system, right? So it's closer to that. You can do stream and batch together. Machine learning is embedded better. So my point is here not to do a feature by feature comparison, because that doesn't make sense. The point is take a look at your use case first. Define the SLAs and these kind of things, and then you can make the right decision where to deploy that. But in general, the overlapping is very small, so for most cases you combine data streaming and data at rest. And so with that, very quick section here, just to make this also very clear, because this comes up so often when I talk to customers, cloud native versus serverless. So when we talk about cloud native architectures, right, all of us talk about Kubernetes today. That's very different than a few years ago, and if you have realized that in the Audi example 5 years ago, they actually run on Mesos at that time. Mesos doesn't exist today anymore, but that in the end at that time was on the same level like Kubernetes, right? It died. Today everybody's using Kubernetes. The point here, cloud native means it's elastic infrastructure, and with that you get a better time to market, you get automation and CI/CD in the platform, decoupled microservice and so on. So that's great, and that's what most people build applications with today. However, when we really then talk about fully managed software as a service, that's even one step further. And this is what many people often underestimate. It's also a part of the reason because some vendors try to trick you, I would say, because not every service that you see in the market that says it's fully managed is really fully managed. What happens in the real world is, and I know the Kafka world best, of course, right? But what I can tell you, if you get a fully managed Kafka service, most of them still just provision the instances to you, start them, and then they hand it over to you for the performance tuning, for the rolling upgrades, for the bug fixes. They even often don't take the Kafka support for you, right? So fully managed or serverless is not often truly that. So that's my point here, and that's the key difference between just a cloud-native architecture on the one side, which is great for building applications, but for the infrastructure itself, and that's true here for Kafka, but in the same way then for Spark with Databricks. That's truly serverless offerings where you can focus on the business logic and not on the infrastructure, because that's where the vendor should take it over for you in the cloud. And with that, let me come to the last section with that. So we have seen the concepts around data at rest versus data in motion and how they play against each other. We've seen a real-world example of connected cars, understand that some of the services are serverless, some others are not. And with that in the last 4 minutes, let's talk a little bit more about these architectures. So global, regional, edge, and all these things. Because all of them are still important, right? And I want to start with one example here. So a few months ago, AWS had an outage, right? So outages happen, but what was the strange thing? The people in the Disney World theme park couldn't enjoy this theme park anymore, which sounds ridiculous, right? But reality was that because Disney is using all of their apps with cloud services, the cloud was down, so you couldn't order food anymore in this theme park, you couldn't go to the fast line anymore because all these systems are running in the cloud actually. And this is a great example to show that not every workload should or will go to the cloud in the future. Sometimes it's for cost reasons, but some other times it's for a better customer experience or for a revenue perspective. And therefore, my recommendation now, when you think about how to build your own Lakehouse architecture, and again, I think it's an architecture, it's not a product, right? And with that, the first thing you should then do for your different use cases you build on top of that is define the requirements, and mainly what's our uptime requirements, how much data loss can we live with, what's the latency requirements, and based on that then, you can decide, should I process the data in motion? Should I put it at rest for analytics? Should I do a combination of that? And maybe then even one step further, should we also do it across different environments? And environments could be hybrid. It could be one cloud but multiple regions for high availability and disaster recovery. It could also be, for example, replication across regions. Like back to the Audi example. Audi has built the connected car infrastructure globally. So this meant they started in Germany, they rolled out to the US. That's easy because if you start on AWS in Germany and then you roll out to the AWS in the US, right? But what do you do in China? In China, there's only Alibaba and Tencent. So that's, by the way, one of these reasons why many of these customers choose technologies like Kafka and Spark, because this is a generic API you can deploy in very different infrastructure. And then you can even deploy that on-premise or at the edge where needed, when you self-manage it there for reasons. So there's many options and reasons why we do data replication. And we have seen this also in the keynote, right, where the delta sharing for Databricks was announced. Here, however, the question you have to ask yourself is exactly the same like for business applications and analytics. Should you do data replication at rest or in motion? There is no single answer to this question, right? So it really, again, depends on the use cases you have. But I can tell you, if you want to do disaster recovery for your instant payments application and deploy it only with replication at rest, and if you have a disaster, then you will have data loss of the payments, right? So it really depends on the use cases you build. And based on that, in a Lakehouse architecture, you can do data replication at rest with something like the data sharing capabilities from Databricks. Or you can do it with data sharing in real time, like with Confluent, where we have a product like cluster linking, which automatically uses the Kafka protocol to replicate data from one Kafka cluster to another one. No matter if it's across the globe or if it's across different clouds or hybrid environments, right? And so you're very flexible, but you need to understand the requirements first to make this right decision, to build your Lakehouse because it's for you, for your business problems. And so for that, my last slide, of course, another important buzzword, right? So I needed to use that in the last slide. A data mesh for decentralized data products. I think this is another very critical discussion, and depending on who you talk to, it's a very different opinion on that. But when people ask me what I see as a data product, of course, on the one side, it's these things you do the analytics in the warehouse, right? Or in the data lake. But on the other side, if we go back to the connected car infrastructure use case, well, when we deploy the predictive maintenance real-time use case that has to run 24/7 for millions of events per second, is that a data product or not? I mean, for me it is, because that's the added value of this use case, right? Because if you would deploy the predictive analytics addressed, it's very often too late for the use case. And this is again therefore my final mark, and I see I have 10 seconds left, so perfect. Really understand the difference between data and motion. It doesn't matter about technology, focus on the business and then make the right evaluations. And in most cases, we combine different products with each other so that we can solve our business problems best. And with that, I'm at the end of the time, so feel free to reach out to me afterwards here, and thanks for coming and enjoy the conference.